We've got Christian here, Christian Marchal, and going to give a talk on is dark matter really necessary? So take it away, Christian.
Yeah, thank you. So, the idea of dark matter goes back to 1933 and was developed by August Vigier, a Swiss astronomer, and as an explanation of the motion of stars and cloud of gas inside galaxies, and also as an explanation of the motion of galaxies inside clusters. You have an alternative explanation, I will not discuss it. You must understand how was astronomy 1 century ago. The Newtonian analysis was considered as alpha and omega of astronomy. It has led to the discovery of planet Neptune. And of course, people of the astronomers of this time were not ignorant of the general theory of relativity, but the relativistic effect, the known relativistic effect were very small. The advance of the perihelion of Mercury, 43 seconds per century, extremely small, and the deviation of light beam and so on. So they think Newtonian analysis. And what is that essential element of that analysis? Consider an n-body problem under the equation of Newton. So we know that there are some general property, such as motion of the center of mass, rectilinear. We will put the origin of coordinates at the center of mass, and integral of energy, integral of momentum. And also this general property related to the kinetic energy, the gravitational potential, H, the energy integral, constant, and I, the semi-moment of inertia. So, the real theorem, also called Lagrange-Jacobi identity, specifies that the second derivative of the semi-moment of inertia is 2t minus u, twice the kinetic energy minus the potential. The potential energy is minus u, so it can with a minus sign there. And this very general property was famous. So consider a case in which H is positive. If H is positive, then the derivative is larger than 2H, and the semi-moment of inertia is K at least as ht squared. It goes to infinity. The system is not stable. Some of the bodies are going to infinity, and generally all of them. So what happens if the energy is negative? Then 2t, t is smaller than u, the difference is h, and 2t minus u may be positive, may be negative. The ratio t over u in the average must be about 1/2 in order to have a stable system. For instance, in the 2-body case, the ratio t over u is given by this expression, about 1/2, with e the eccentricity of the elliptic motion, and capital E the eccentric anomaly. So it goes up and down about 1/2. And at this time, the measure the evaluation of that ratio T over U, where the expression T over U for a lot of clusters, T over U was over 10 and over even 25. So how can a system be stable in their mind with such a large kinetic energy and a small potential, gravitational potential? Thanks to this astronomer with their Newtonian orientation, they don't think that the relativistic effect can be dominant. So the dark matter hypothesis was very natural. We will use standard cosmology, but this can be studied in many different cosmologies. The ratio T over U is so large that the gravitational effects are very small, and we can study the free motion in an expanding universe. The gravitation will be a small plus for the stability, and that's all. So the real question: is the dispersion of cluster faster or slower than the expansion? That's the true question. So we will use the Commonwealth system and have, you have there the classical Friedman metric with the interval. ds is the proper time of something that makes the differential dt, dA, dphi, df. Classical. S proper time, t plus quicker time. R, the radius of universe, are radial parameter, latitude and longitude, the usual expression. And it gives this u, that parameter u is either sin h or sin a according to the shape of universe, open, flat, and closed. In that case, it's a sphere, a hypersphere, with the usual coordinate on a hypersphere, the angle A, the colatitude phi, and the longitude L. You have here the evolution of the radius, the quantity R that is called radius of universe, and that is really the radius of universe in a closed case, since it is a hypersphere. And you have the Friedman-Lemaitre equation for this evolution. Rho zero is present average density of universe there, and R0 present radius of universe. We have there the cosmological constant of Einstein, and that ratio is called density. It is a density of energy, and it is called, I don't know why, density of energy of what vacuum. If this was true, the density, the total energy of universe will increase with the expansion, and the conservation of energy will be no more true. So, as suspect, it's just an idea and not a reality. Yeah. So we will do the analysis in a flat universe, but it's very close to that analysis for the other case. In that case, the common coordinate x, y, z, Cartesian common coordinates are given by this expression, and the vector r is x, y, z. the expression of the metric of universe is given by this, and the free motion with constant vector r and the constant b are given by that. So the vector r has an evolution given by this expression. In the case b equals 0, we have a straight line with a velocity c at our time and proportional to c. That means c at any time for people living at this time, in a constant direction. For the very large b, we have small velocities. And we say that the velocity decreases as the inverse of the square of the radius of universe. It decreases very rapidly. And so the dispersion is not a constant. We must understand our way of knowledge of universe. And from the most accurate to the last one. The best mean of analysis is the spectroscopy. It gives the Doppler effect, the chemical analysis of the star, and so on. Photography and angular measure are also very accurate, giving the luminosity at various wavelengths. Evaluation of distances are much less accurate. There are different means of analysis, the redshift, of course, which is, we must take account of the proper velocity. Cepheids, error, Leray, and so on, many means of analysis that doesn't give exactly the same result. And so the measure of distances is much less accurate than the other two. After that, our knowledge of the evolution of star, our knowledge of the other cluster and the corresponding statistic, information related to general theory of relativity. For instance, the lensing effect, which is very interesting when it's possible to have something accurate there. And general information related to cosmology, of course, this is not accurate at all. An example, the famous Virgo cluster, probably the most famous of clusters. About 2,000 galaxies, a distance of 54 million light years. Transversal diameter, the one you can measure on picture, about 40 million light years. Radial diameter, by measure of distances, about the same length, about. With most redshift measure correspond to this length, but a few persons disagree. We must consider the picture of the measure of redshift, not velocity. You have the redshift there, and the number of stars in a given square degree of space. And it gives something like this. And so on. So we suspect that this is a cluster. We suspect. And it has some dispersion of velocities. That dispersion is generally in agreement with the transversal diameter. But a few are outside. We don't know if these few belong to the cluster or belong to some galaxies farther away or in front. It's a very difficult analysis.
Are there as many further than nearer in that? Because some of these correspond to further rather than nearer.
Yeah.
Roughly the same number?
But the proportion is about 3, 4, 5%.
But 2.5% further,
Yeah.
2.5% nearer.
Yeah. So it may be true that the cluster are losing some galaxies in the billion of years. Yeah, that's possible. So we have several, not many, but several possibilities of evaluation of the total mass of the cluster. Evaluation through the luminosity. Evaluation through the Vigier theorem. It gives sometimes 100 times more, but usually 30 or 40 times more. Evaluation with a lensing effect if it exists. Evaluation with an X-ray observation of hot gas. And today, we know that these two evaluations are very similar when they are possible. The ratio is not 1, but it is between 1/2 and 2. So it's much better, and the best method governs the other one. So, and this evaluation is in between the other two. And you must understand how difficult it is. For instance, evaluation of the mass of the Milky Way. When I was a boy, long time, the Milky Way was estimated to be 1 million solar mass. 1 billion solar mass. 20 years later, it was 20 billion solar mass. In the year 1990, it was about 100 billion solar mass. And today, 250 billion solar mass. So, even for the Milky Way, the nearest galaxy, it's very difficult to know the mass. And other point, the Andromeda galaxies that belong to the local cluster is approaching at the velocity of 120 kilometers per second. Its distance is 25 million light years. So it means that the collision between our two galaxies will be in 6 billion years. Evolution in a cluster is extremely long. It takes cosmical time. Conclusion. The study of cluster remains very difficult, but at least the Vigier theorem was very misleading, and the relativistic effects are dominant. The evolution of clusters requires billions of years, and the dark matter may exist after all, I don't know. It's a measure of our ignorance, because anytime there is something we don't understand, people claim it's dark matter, property of dark matter. But it is not at all mandatory. The cluster and also the galaxies themselves can be explained without dark matter. Thank you.
Thank you. Any questions? Yeah.
I like to talk with the board. Thank you. Can you, on the galaxies and the redshifts, not quite related to this talk, can you comment on how Alton Harp's work regarding the anomalies of redshifts, where he questions where he has redshifts in a cluster or in a galaxy that don't, which make these clusters cigar-shaped.
When you have a big cluster somewhere, most of its stars have redshift corresponding to the distance of the cluster. Of course, these stars have, in spite of that, they have proper motion. They are not at rest in the chromobile system. But if they are further away, their redshift corresponds to a smaller distance, and they are coming back. If they are too near, their redshift corresponds to such a distance, so they are moving away. So in both cases, they are approaching the redshift distance. So the system is stable, at least in the radial direction. But if it is stable in the radial direction, it's certainly also stable in the other direction. Yeah.
But some of these redshifts are fractions of the speed of light.
Yeah.
So that's a big fact.
Oh, but the correction number is more.
Okay.
It's okay. Okay, you're talking about the fingers of God, are you? They're called the fingers of God.
No.
No. Anything else?
Well, I've got another question.
Go ahead. Oh, I hope I can understand it.
With the expansion of the universe, does that also imply that galaxies are expanding? Because I heard that argument that galaxies are not expanding because their gravitational, the galaxy is such that the Milky Way is not getting bigger as the universe is expanding.
Yeah.
Can you give something on that argument?
Yeah, the dynamics of the galaxy we visited have already studied the case of galaxies. In galaxy also we have a problem of equilibrium, and we don't know if galaxies are expanding as the universe. That's we don't know. And but we suspect that the star, you consider the very famous analysis here you have the velocity measured by Doppler piezo effect, and here the distance from the center of the galaxies. So the velocity measured are something like this. And the velocity suspected with the Newtonian analysis must be something like that. It begins very close, but it goes down. So the difference is suspected to be the effect of dark matter. So I have studied that. In the case of galaxies, the relativistic effect remains extremely small because the distances are negligible. And what is the most important? The most accurate effect measure is that of spectroscopy. We have, and it's not the picture of the galaxies that give us very accurate information. And we obtain this. It is possible to have a repartition of stars such that this part is respected up to the final massive presence of stars. But after that, the Newtonian analysis can give this. How can we measure these velocities are beyond the massive presence of stars? We measure it through the measure of cloud of gas. And that means that I have some picture of galaxies. It means that outside the massive presence of stars, the cloud of gas are escaping. So we have not the necessity of dark matter if we allow a not strict equilibrium with a loss of cloud of gas in outer space. Exactly as in the solar system, we have permanently a loss of solar wind at a rate of several million of tons per second. But in the history of the solar system, it is a loss of 0.03% in the whole the life of the sun. And it will be a kind of thing like similar in the history of galaxies. So, yeah.
Sorry, we finished that. I was going to say, the talk about dark matter is that it's a sphere surrounding a galaxy. A sphere, a uniform sphere around a galaxy.
Oh,
the galaxy isn't a plane.
Yeah.
I mean, that just seems to be nonsense dynamics to me. How can you have a sphere of dark matter, stable with a galaxy in planar orbit?
But the galaxies are very flat.
Yeah, they're flat.
Yeah.
So how can you have a sphere of dark matter in a stable dynamic
Oh,
equilibrium?
the clusters. We have it because it's easier to compute.
But it's surely dynamical nonsense.
Yes, I agree.
But can be.
Are the clusters that flat?
Peter, I think this can be answered. That can be answered. There's a very simple answer to dark matter, and we have a good example of it. If you follow what I've also mentioned, the Lorentzian version of relativity, then gravity does not depend on mass, but every elementary particle makes the same contribution to the gravitational field. That means also photons make a contribution. And the good thing about photons in a galaxy is that they have that distribution which we need to have these flat curves in galaxies, this flat rotation curves, yeah. And of course the photons which spread out are on a sphere. They are not flat. The stars are flat, but the photon distribution is not flat. Yeah. And we have another example which is very well, fits very well to it. It was just detected new galaxy, a galaxy which has very little light, which is very dark, by more than a factor 200 compared to others. And the dark matter is also down by about a factor 200 with respect to other galaxies. So we have a lot of hints that dark matter is photons. And the question of
what's the question?
Peter Roland, yeah. Just it was a comment to the question of Peter Roland. He does listen, but okay.
Any comments, questions? Thank you very much.
This is an island that is
I think I have it already. Yeah.
copy of the galactic mass? I'm very fortunate, thank you.
Stand down now, lunchtime.